Hello everyone, this is lecture 2 on system of linear equations. In this lecture I will discuss following topics: elimination method, system in triangular form, echelon form, pivot and free variables, Gauss elimination method, row canonical form, rank of a matrix. Elimination method is very basic. There are merely two steps. Consider the system of equation given by 1 and 2. 2x minus 3y equal to minus 8, 3x plus 4y equal to 5. So we solve this problem by elimination method. So from equation 1 and 2, we suitably apply operations and eliminate one of the variables x or y. So I am here applying elementary operations. For example, multiply first row by 3. I will get equation number 3. 6x minus 9y equal to minus 24. Now multiply second equation by minus 2. We will get equation number 4. Minus 6x minus 8y equal to minus 10. Now if you see this equation 3 and the next equation 4, we add them and finally this x will cancel out and we have equation minus 17y equal to minus 34, which implies that y is equal to 2. Once we have value of one of the variables, we use back substitution and now substitute the value of y in any of these two equations, equation number 1 or equation number 2. Here I am using equation number 1. So from equation we have 2x minus 3 times y and now y is 2. So we get from this x is equal to minus 1. So finally we have a unique solution for this system of equations. X is minus 1, y is 2. Consider the geometrical view of this example. 3x plus 4y equal to 5, the red line, and the blue line 2x minus 3y equal to minus 8. These two lines have different slopes, so definitely they will intersect at a point and that point is minus 1 comma 2. So this is the solution of your system of equations. Next example is for the situation where we have no solution. So consider equation number 5, x minus 3y equal to 4, and equation number 6, minus 2x plus 6y equal to 5. Now we use the first step, forward elimination. Apply elementary operations to these equations. So I am multiplying equation number 5 by 2. I have equation number 7, that is 2x minus 6y equal to 8. Now add equation number 6 and equation number 7. We have following equation: 0 times x plus 0 times y equal to 13. Now x and y are real numbers, so left hand side is always 0. This implies that 0 equal to 13, which is not possible. So we say that the system has no solution. And if you see the system, these two equations, they have same slope, but they have different y-intercepts. So let's see the geometrical view for this problem. As I explained earlier, you can see from the graph, these two lines, minus 2x plus 6y equal to 5, represented by red color, and the next is x minus 3y equal to 4, represented by blue color. So these two lines are parallel, but they have different y-intercepts. So we can say that they are never going to intersect at a point. So we say system has no solution. Consider example number 3. When we have infinite solutions for a given system of equations. So equation number 8, x minus 3y equal to 4, and equation number 9 is minus 2x plus 6y equal to minus 8. So we apply the first step, that is forward elimination. I will multiply equation number 8 by 2. I will get equation number 10. 2x minus 6y equal to 8. Now add equation number 9 and 10. I will get 0 times x plus 0 times y. This is equal to 0. And if you recall the result from lecture number 1, this is a degenerate equation. And if in degenerate equation, right hand side is 0, then every real number is a solution of this system. So here I am saying that for every value of x and y, this equation 0x plus 0y equal to 0, it is always satisfied. So we say that the system has infinite number of solutions. In the situation of infinite solutions, we can represent the solution in two forms, free variables or the parametric form. Here I am using parametric form. So let x be t, where t is any real number. Then from equation number 8, we can find out the value of y, and it is given by t minus 4 divided by 3. So the solution is x equal to t, y equal to t minus 4 divided by 3, where t is any real number. Now here I am putting x equal to t. You can put y as any real value. For example, y is t star, where t star is any real number. Then again, from using equation number 8, we have x as 3t star plus 4. And finally the solution is y is t star, x is 3t star plus 4, and t star is any real number. Here I am using equation number 8, but there is no restriction. You can use equation number 9 also. We can have little different form but the same solution. Next one is definition, a system in triangular form. Consider this system given by these four equations t dot 1 to t dot 4. We have 2x1 minus 3x2 plus 5x3 minus 2x4 equal to 9, first equation. Second equation is 5x2 minus x3 plus 3x4 equal to 1. 7x3 minus x4 equal to 3, and 2x4 equal to 8. So such a system is called triangular system. In these equations, x1, x2, x3 and x4 are leading variables. Now what are the properties of a triangular system? In the first equation, the first unknown is x1, this is the leading unknown. In the second equation, the second unknown x2 is the leading one, and so on. In the third equation, the third unknown, that is x3, this is the leading unknown, and so on. So it means all the variables appearing in the system, they are leading variables. Thus the system is always a square system, and each leading unknown is directly to the right of the leading unknown in the preceding equation. Such a triangular system always has a unique solution which can be obtained by back substitution. Now we use back substitution method and find out the solution of this triangular system. From equation t dot 4, we can directly find out x4, which is 4. Now using the value of x4 and equation number 3, that is t dot 3, we can find out x3, which is 1. Now using equation number 2, t dot 2, and the values of x3 and x4, we can find out x2, which is now minus 2. And finally, from equation number 1, t dot 1, and using the values of x2, x3 and x4, we have x1 equal to 3. So finally, the solution of the triangular system is 3, minus 2, 1 and 4. Now I will discuss few definitions: echelon form, pivot and free variable. Consider the following system of equations defined by equation number 11, 12 and 13. This is a system of three equations in 5 variables x1, x2, x3, x4 and x5. If is equation number 11, the first non-zero term is 2x1. In equation number 12, we have x3, and in equation number 13, we have 3x4. So this above system represented by equation 11, 12 and 13 is in echelon form. So we can define now echelon form as: no equation is degenerate. The leading unknown in each equation other than the first equation is to the right of the leading unknown in the preceding equation. For example, in equation number 12, the leading unknown is x3 and it is towards the first leading unknown in equation number 11, which is x1. Here x1, x3, x4 are leading unknowns. We call them as pivot variables. And the remaining variables, that is x2 and x5, they are called free variables. This is the general echelon form where we have n variables and the system of equations. It has r equations, x1, xj2, xjr. These are leading unknowns, and they are such that these ji's, they satisfy the following condition, that 1 is less than j2 is less than j3, and so on. And a11, a2, j2, and ar, jr, the coefficient of these variables x1, xj2 and xjr, they are not 0. Here these variables x1, xj2 and xjr all are pivot variables, and the remaining are free variables. Here it is very important to note down that r is less than or equal to n. The system of equations is always less than or equal to the number of variables. Consider these examples for more clarity about these definitions, pivot variable and free variable. Consider first system A. We have 3 equations and 5 variables. So first check whether this system is in echelon form or not. First equation is 2x1 plus 3x2 minus 6x3 minus 5x4 plus 2x5 is 7. Next is x3 plus 3x4 minus 7x5 equal to 6, and x4 minus 2x5 equal to 1. So here first condition is satisfied, that there is no degenerate equation and every leading unknown in any equation is to the right of its preceding one. Here x1, x3 and x4 are pivot variable or leading unknowns, and the remaining variables, that is x2 and x5, are free variables. Consider system number B. These are 3 equations in 3 unknowns x, y and z. If we talk about the system in the current form, it is not in echelon form. And if it is not in echelon form, then we cannot talk about free variables and pivot variables. Consider system C. Again we have 3 equations and 3 variables x, y and z. And if we see this one, there is no degenerate equation, and the second condition, that each leading unknown in the equation is to the right of its preceding equation. So that condition is also satisfied. So we say that the system is in echelon form. And from the first equation, x is the leading variable. From the second one, y is the leading variable, and from the third, z is the leading variable. So x, y and z all are pivot element, and there is no free variable for the third system C. This is very important theorem about the solution of a system of equations when the system is represented in echelon form. So consider a system of linear equations in echelon form, say R equations in n unknowns. Then there are 2 cases. If R is equal to n, that is, the number of equations is equal to the number of unknowns, then the system has a unique solution. And in this case, the system is going to be triangular system. Second is, number of equations is less than the number of variables, that is, R is less than n. In that case, system has infinite solutions. Now in this case, how to find out the solution? We have R variables as pivot variables and n minus R variables are free variables. So we can assign arbitrary values to these n minus R free variables, and then we solve uniquely for R pivot variables to get the solution of the system. For the second case, when the system of equations has a infinite solution, then we can represent the solution in 2 forms. One is parametric form and second one is free variable form. Now consider this example. It is a linear equation in 3 variables x, y and z. We can represent this equation in echelon form as 3x plus 2y minus z equal to 3. So here 3x is the first unknown, that is the leading unknown. We call this one as the pivot variable, and y and z, they are free variables. So according to the theorem, we can assign any real value to these free variables. So let y be t and z be s, where t and s, they are real numbers. Then using this equation, we can have x as 1 minus 2 by 3 t plus 1 by 3 s. So the parametric representation of the solution is defined as x is 1 minus 2 by 3t plus 1 by 3s, y is t, z equal to s, where t and s, they are real numbers. Here it is very important to note down that out of these three variables x, y and z, we can take any of the variables as the pivot variable, and the remaining two variables we assign them as free variables, and then correspondingly we can find out the solution depending upon the free variable and the pivot variable. Consider this example represented by a system of three equations in 5 variables x1, x2, x3, x4 and x5. From the system we can see that it is in echelon form with x1, x3 and x4 as the leading unknowns or the pivot variables, and the remaining variables, that is x2 and x5, they are free variables. So to find out the solution of this system, we can assign free variables any real value. So let x2 be s and x5 be t, where s and t, they are real numbers. So now using these equations, we can find out the values of these pivot variables. So starting from the last equation, 3x4 minus 9x5 equal to 6. I will put x5 as t, and finally I have x4 as 2 plus 3t. I can divide by 3, so I will get x4 as 2 plus 3t. Now we substitute the values of x4 and x5 in the second equation, and we can find out x3, and it comes out to be 1 minus 8t. Now we have x2, x3, x4 and x5. Using the values of these variables, we can find out x1 from the first equation, and it comes out to be 4 minus 3s minus 9t. So this solution is called parametric form of the solution, and I am representing this by a vector u as 4 minus 3s minus 9t, s 1 minus 8t, comma 2 plus 3t, comma t, where s and t, they are real numbers. We can represent the solution in terms of free variables also. So in this case, we are not doing anything new. We just keep the same solution, but we keep the free variables as they are rather than assigning them any values as t or s. So if you see the parametric solution on the previous slide, in the free variable form, I am just writing the values of these variables x1, x2, x3, x4 and x5 in terms of free variables, that is x2 and x5. Consider following two system of equations represented by system A and system B. Now question is, out of these two systems, which system is easier to solve algebraically? And if you see carefully, the system B can be solved easily. From the last equation we can find out z, that is 2. Now we use back substitution. From equation number 2 we can find out y. Once we have y and z, then from equation number 1 we can find out x. Now we see that the system B is in triangular form. Gauss elimination method. It consists of two parts. First is forward elimination and second one is backward elimination. In forward elimination, step-by-step reduction of the system yielding either a degenerate equation with no solution or an equivalent simpler system in triangular or echelon form. After reducing the system in triangular or echelon form, we use step-by-step back substitution to find out the solution of the simpler system. The main difference between Gauss elimination method and just elimination method is that in Gauss elimination method, we reduce the system in triangular or echelon form. We don't have this condition when we apply elimination method directly for a given system of equations. So consider a system of m equations in n variables. Here matrix A is Aij m times n. This is the coefficient matrix. If m is equal to n, that is number of equations is equal to the number of variables, then this A is called a square matrix, and this is the given system of equations, m equations and n variables. This given system of equations can be represented in the matrix form as Ax equal to B, where A is m cross n matrix. The variables x1, x2, xn, they are represented by vector capital X, and the constant terms on the right hand side b1, b2, bm, they are represented by the vector b, that is capital B. Now these two matrices A and B, they can be represented just by one matrix, that is A, B, which is called augmented matrix. Definition of a row echelon form or echelon matrix. A matrix in row echelon form has the following properties. First, all rows consisting entirely of zeros occur at the bottom of the matrix. Second property, each leading non-zero entry in a row except the first row is to the right of the leading non-zero entry in the preceding row. Consider the following matrix A. This is in echelon form. In the first row, the leading non-zero entry is 1. In the next row, the leading non-zero entry is 3, and it is appearing to the right of the first non-zero entry in the first row. Similarly, in the third row, the leading non-zero entry is 4, and it is to the right of second row with leading non-zero entry as 3. Similarly for the fourth row and the fifth row, all these conditions are satisfied. And if you see this one, then the first column, the leading non-zero entry is 1, and all the entries below this are 0. Similarly for the second row, leading element is 3, and all the entries below this are 0. Similarly for the third row, non-zero element leading 1 is 4, and all the entries below 4 are 0. Similarly for the fourth row, the leading non-zero entry is 7, and below this we have 0, and for the last one we have leading non-zero entry as 3. So this is the main point for the echelon matrix. Consider this example, a system of 3 equations in 4 variables x1, x2, x3 and x4. I am denoting these equations by L1, L2 and L3. We can represent the system of equations in matrix form, where the first one 1, 3, minus 2, 5, 2, 8, minus 1, 9, 3, 5, minus 12 and 17. This is 3 by 4 matrix, and we call this one as the coefficient matrix. Next is a column vector x1, x2, x3, x4. These are our variable vector. Next one is 4, 9, 7. This is the right hand side vector. So last one is the representation of given system of equations in matrix form. Now we solve the system of equations by Gauss elimination method. So the first step is forward elimination. For this one, we convert the system of equations in echelon form. So we use the coefficient 1 of variable x1 in equation number 1, that is L1, as the pivot one, and we eliminate x1 from the second equation L2 and third equation L3. For this one I am applying the elementary operation. Change second equation to second equation minus 2 times first equation. You can see the calculation 1. After applying this operation, the second equation reduces to 2x2 plus 3x3 minus x4 equal to 1. Now we reduce third equation, that is L3, and for this one we apply the operation L3 minus 3 times first equation L1. When we apply this one, after this operation, the third equation reduces to minus 4x2 minus 6x3 plus 2x4 equal to minus 5. Now this is the form of equation 1, 2 and 3 after eliminating x1 from the second and third equation. Now in the second equation, the pivot element is x2. Now using this second equation, we eliminate x2 from the third equation, that is L3. For this one, we apply the elementary operation, change L3 to L3, that is third equation, plus 2 times second equation. When we apply this operation, we will get the following equation: 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 equal to minus 3. Where these x1, x2, x3 and x4 are real numbers. So if we see this equation, left hand side is always 0 and right hand side is minus 3, which is not possible. So we say that this system has no solution and we just stop the process here. Consider example number 7. Now we solve this again by Gauss elimination method. We have 3 equations L1, L2, L3. It is a system of 3 equations in 3 variables. Now we apply elementary operations and we reduce the system into echelon form. So first I will eliminate x from the second equation L2 and third equation, that is L3. So we apply following operation. Change second equation as sum of second equation and first equation, and third equation will be third equation minus 2 times first equation. So after reducing this one, we keep the first equation L1 as it is, x minus 2y plus 3z equal to 9. After applying the elementary operation L1 plus L2, second equation reduces to y plus 3z equal to 5, and third equation reduces to minus y minus z equal to minus 1. So now x variable has been eliminated from L2 and L3. Now we again apply elementary operations and we eliminate y from the third equation L3. To eliminate y from the third equation, we apply the following operation. Change L3 to sum of L3 and L2, that is we add second and third equation. So finally equation 3 is given by L3, that is 2z equal to 4. Now if we see these 3 equations, first one is x minus 2y plus 3z equal to 9. Second equation is y plus 3z equal to 5, and third equation is 2z equal to 4. So now the system is in echelon form. We can use back substitution and we can find out the values of these variables. So from the third equation, we have z equal to 2. Now after calculating z, we use second equation and we can find out the value of y by substituting z equal to 2. So finally y is minus 1. Now z is 2, y is minus 1. We use first equation L1 in this echelon form and we can find out x, and x is 1. So finally this answer is x equal to 1, y equal to minus 1 and z equal to 2. Now we discuss row canonical form. A matrix A is said to be in row canonical form if it satisfies following conditions. First, all rows consisting entirely of zeros occur at the bottom of the matrix. Second, each leading non-zero entry in a row except the first row is to the right of the leading non-zero entry in the preceding row. Third, each pivot, that is leading non-zero entry, is equal to 1. And fourth, each pivot is the only non-zero entry in its column. So if you see first two conditions, they are exactly the same as in the echelon form. So row canonical form is a special type of echelon form with two additional conditions. Condition number 3, that is each pivot element is 1, and fourth one, that each pivot is the only non-zero entry in its column. Zero matrix and identity matrix of any size are important special examples of row canonical form. Consider these examples. We will check whether the given matrix is in echelon form or in row canonical form. If you see the first matrix A, it satisfies first two conditions, that all the rows having only zero entries, they occur at the bottom of the matrix, and every non-zero element, that is the leading element in any row, is to the right of its preceding leading element. So in the first row 2 is the pivot element, in the second row 1 is the pivot element. I have circled all the pivot elements. So the matrix A is in echelon form. Now we check whether this one is in row canonical form. The third condition is that each pivot element in row canonical form is 1. But here we have 2 and 6. These are pivot elements and they are not equal to 1. Also here fourth condition is also not satisfied. Matrix A is in echelon form, but it is not in row canonical form. Now come to the next example, B. It is a 3 by 3 matrix. It is in echelon form because only first two conditions are satisfied. Here 2 and 1 are pivot elements, but here third condition of row canonical form is not satisfied. Even fourth condition is also not satisfied. So B is again echelon form but not in row canonical form. Now consider matrix C. This is in echelon form because first two conditions are satisfied, although there is no row having all entries as 0. Now here 1 1 1, you can see the circle term. These are the pivot elements, all of them they are 1. Now if we see the second column, it has a 1 pivot element and all other entries in the second column they are 0 except the pivot element 1. Now in the second row 1 is the pivot element, and corresponding to this 1, the fourth column, all other entries are 0. In the third row 1 is the pivot element, and corresponding to this 1 we have fifth column and all other entries are 0 in this column. So we can say that matrix C is in row canonical form. Now I will discuss a numerical problem to find out the way to reduce a given matrix to row canonical form. Here A is a 3 by 4 matrix. So I will start with the first row. Check that first entry is non-zero. If it is non-zero, then you can interchange with any other row. So here I am representing rows by R1, R2, R3. R1 is first row, R2 is second row, and R3 is third row. So now using the first entry, which is 1 in the first row, I will make all the other entries in the first column 0. For this one I will apply elementary row operations. So for the second row I am applying the operation second row minus 3 times first row, and I am representing this as R2 goes to R2 minus 3 times R1, and for the third row I will change it to third row plus 2 times first row. So I have circled the first pivot element as 1 in red color. I will apply the operation, these above two operations, and finally the matrix reduces to 1 2 minus 1 1, first row as it is. Now second row is 0 minus 4 8 minus 1, third row is 0 5 4 3. Now in the second row the next pivot element is minus 4. So reduced it to echelon form, we make this entry as 1. There are two options. First is I can divide second row by minus 4. In that case, second row reduces to 0, 1, minus 2, 1 by 4. There is one more option. In this way, we can avoid fraction numbers in the matrix. For example, we can apply one operation, change R2 second row as sum of second row plus third row. In that case, second row will be 1, 12 and 2. But in the current problem, I am dividing second row by -4. So we have the matrix as first row is 1, 2, -1, 1. Second row is 0, 1, -2, 1 by 4. Now in the third row, we have 0, 5, 4 and 3. Now we make the third row entry 5 as 0. For this one, I am applying operation. Third row goes to third row -5 times second row. So see the last matrix. After applying this operation, we have third row as 0, 0, 14 and 7 by 2. Here I am making the second entry in the first row 0, so that the second column we just have pivot element 1 and all other entries are 0. So I am applying the next operation, change first row to first row -2 times second row. So the first row reduces to 1, 0, 3, 1 by 2. Now here I am converting it in row canonical form, and I am changing all the entries in a particular column containing pivot element as 0. There are two ways. We can do it simultaneously along with this row canonical form part, or first we can reduce the system, your matrix, in row echelon form, and then we apply suitable elementary operations to make all other entries 0 except the pivot element. After applying all these elementary operations, now we have matrix A is equivalent to 1, 0, 3, 1 by 2. Second row is 0, 1, -2, 1 by 4. And third row is 0, 0, 14, 7 by 3. So in the third row, 14 is the pivot element. So we divide by 14 and we make this entry as 1. So I have next matrix. First two rows are as it is. And now the third row is 0, 0, 1 and 1 by 6. Now if you see the third column, except the pivot element 1 here, we have two other non-zero entries, 3 and -2. Now we apply suitable elementary operations and we reduce these entries to 0. So we are applying following operation, change R2 to R2 plus 2 times third row. And for the first row, we apply the following elementary operation, first row -3 times third row. Now the first row is 1, 0, 0, 0. Second row is 0, 1, 0, 7 by 12. And third row is 0, 0, 1 and 1 by 6. So there are 3 pivot elements. We can see I have circled them. And all other entries in these columns except the pivot 1, all are zeros. So this is the matrix in row canonical form. A system of linear equations can be completely represented by its augmented matrix. So various elementary operations which we perform on the system of linear equations, now they can be performed on its augmented matrix. So now I'm just rewriting those operations in the form of matrix and its rows. So suppose we interchange ith and jth rows of a matrix, then we represent it as Ri, left right arrow, Rj. Second one, if we replace ith row by a non-zero multiple of k, where k is any scalar, then we say Ri, right arrow, k times Ri. Now if we replace jth row by the sum of itself and scalar multiple of ith row by some scalar k, then we say Rj is going to Rj plus k times ith row, that is Ri. A matrix A is said to be row equivalent to another matrix B if matrix B can be obtained from A by a sequence of elementary row operations. In the case that B is also an echelon matrix, then B is called an echelon form of matrix A. We can represent a system of equations by its augmented matrix. So we can check the consistency or inconsistency of the system just by looking at its augmented matrix. For this, we need to define its rank. So what is the rank of a matrix? The rank of a matrix A is equal to the number of pivot elements in the echelon form of the matrix A. Consider the example, matrix A. It is already in the echelon form, and we can see from the matrix there are 3 pivot elements. So we say that rank of the matrix is 3. Now consider next matrix B. Again it is in echelon form and there are 2 pivot elements. So we say that rank of the matrix B is 2. Consider matrix C. It is in row canonical form. You can see there are 3 pivot elements. I have circled them. Except this pivot element, all entries are 0 in these columns. So depending upon the pivot elements, rank of the matrix is 3. Now there are various ways to find out the rank of the matrix, but all the definitions or the ways lead to the same number for the rank of a given matrix. Now I am defining the rank of a matrix in terms of minor. The rank of a matrix is the maximal order of a minor of a matrix, say R not equal to 0, and all minors of the R plus 1th order and above are equal to 0 or they do not exist. It means there exists at least one minor of order R which is non-zero, and all minors of order higher R plus 1 or above are equal to 0 if they are existing. So if we have a matrix of order m by n, then rank of the matrix is always going to be less than equal to minimum of m and n. Consider this matrix 3 by 4. So it is clear that the rank of the matrix is going to be less than or equal to the minimum of number of rows, that is 3, and number of columns, which is 4. So the rank of this matrix A is less than equal to 3. So I am starting with the largest minor of order 3. So I am taking first 3 columns. Its value is 0. So we look for another minor of order 3. So I am taking second, third and fourth column, and value of this minor is 2, which is non-zero. Here we cannot have a minor of order 4 because the number of rows is 3. We can't talk about minor of order 4 by 4. So here we can conclude that rank of the matrix is 3.